Welcome to Mastering Solutions. In this question, they tell us that we have this glass here, so I've drawn that for us already, and it's 1.2 centimeters thick. So we have 1.2 times 10 to the negative 2 meters for its thickness. And we're told that the light is incident on the glass at a 35-degree angle. So the angle of incidence is always from the normal to the ray. And so here is our normal. So this angle here is going to be 35 degrees. The light is going to refract because we have an n of 1 and an n of 1. Let's say it's glass, they say, so 1.50. And so we're going from a low to a normal index of refraction, so it'll refract towards the normal. And then this here is some angle, we'll say theta sub g. And so we're trying to figure out how far is it in the glass before it comes out on the other side right here and refracts like this. And so this distance is what we're trying to solve for. If you imagine, if we carried this down, we could create a right triangle right here. And so here's our right angle. And so the hypotenuse, you can see, is what we're trying to solve for. So here's our redrawn right triangle, and this distance, we'll say x. That's what we're ultimately trying to solve for in the question. To do that, we need to use Snell's law to figure out this angle right here. We know that Snell's law is n1 sine of theta 1 is equal to n2 sine theta 2. And we can replace the n1 and the theta 1 into theta 2 with what they are. We'll say air and glass, right? So n of the air is equal to sine of theta in the air, and n of the glass is equal times the sine of the theta of the glass. And remember, we're trying to solve for this. So if we isolate that, we can do that by dividing both sides by n of the glass, and then we'll take the inverse sine of both sides of the equation. Let's say theta glass is equal to the inverse sine of n of the air times sine of theta in the air divided by n of the glass. Now I drew it like this because you could also isolate them like that. It's the same thing, just notated slightly differently. Theta in the glass will be equal to the inverse sine times n of the air is 1 times sine of the angle in the air, theta of the air, is 35 degrees. And that will all be divided by the n of the glass, which is 1.50, of course. So we have the inverse sine of 1 sine of 35, and then that's divided by 1.50. So our angle in the glass is 22.48 degrees. So we'll round that to 22.5. So 22.5 degrees. And that's an intermediate answer. That's not what we're trying to solve for, as we talked about a minute ago. We need this distance here. So this angle is the angle we just found, the theta of the glass. And we're told that this distance, the height of the glass, is 1.2 centimeters. You could also move the decimal place over 2 places. I find that's more prone to error, so I like to do it this way. I think it's a little easier. And so we have the adjacent, and we have the angle, and we need the hypotenuse, so we'll be using cosine. So cosine of theta is equal to the adjacent over the hypotenuse. And we need the hypotenuse, so we'll multiply both sides by h and then divide over cosine of theta. So let's come over here. So we have h is equal to the adjacent divided by cosine of the angle. The adjacent, as we just talked about, is 1.2 times 10 to the negative 2 meters divided by the cosine of the angle, which we found is 22.5 degrees. 1.2 times 10 to the negative 2 divided by the cosine of 22.5. So the distance of how long it'll be in the glass for is, this is meters, so 0.013. So 0.013 meters. We can move the decimal place 1, 2, and we have 1.3 centimeters, for the distance of how long the light ray travels through the glass.